Hello, Julian. I told you I was going to make you some short videos trying to teach you some really cool things with the ham radio so that you can take them with you when you take your test. You can learn something, but also when you get out there, this is practical stuff that you'll need. So here's what I'm going to be doing. I'm working with Yagis today. I'm going to be making some changes with this Yagi so that I can make it from a vertically polarized antenna to a horizontally polarized. And in essence, all I'd have to do is just take the beam and turn it to where these elements are pointing horizontal. But then they wouldn't fit the bracket. The clamp goes around the mast and through these holes right here. Okay, so what I'm going to do is I'm going to drill 2 holes up here so that when this thing turns on its side, on the horizontal side, I can clamp it to the mast and we'll have a horizontally polarized antenna. First of all, the Yagi has some different parts to it that you'll see in your test. It has a driven element, a reflector element, and director elements. And to show you the difference, if you look right here, the coax, the feed, is coming up here, and it terminates at this element right here. Well, this is your driven element. This is the element that actually emits the signal. Now, since it is a beam, it's directional and goes in the direction that you point it, primarily. So, that being said, this is your driven element. And then this is something else, and I'll talk about it when I know more what I'm talking about, okay? Right now, don't worry about that. But this is the driven element. And then if you look back here, this is the last element on the boom. And since this element, or this beam, is pointing that way, this is the reflector element, the reflector. And then if you go out this way past the driven element, now you've got your director elements. And if you'll notice, this Yagi is a 1, 2, 3, 4 element Yagi, and so it's pointing in that way, and the signal will radiate from the director and go out that way. This is the excuse me, the reflector, I believe is what it's called. Now I'm trying to think. It's the reflector element, I do believe, but you get the point. This is reflecting the signal out that way, and then these are directing the signal on out that way, in that direction. So now if you notice, look at the length of this element. If you check that element, I'll bet you it's about 18 inches. And let's see. Yep. Right close to it, right close to 18 inches. And that's the proper length for the wavelength of 2 meters. And you'll have to get into your calculations. And the one that you'll have to know for the test is the wavelength calculation. Okay, so, but what that means is the longer the element, the longer the wave, and the lower the frequency, okay? So this is 18 inch long element, and if you do all the math on that, it comes out to 2 meters. And this is a 2 meter beam, 4 element Yagi, and right now it's on the vertical position. And what that means is that you've got vertically polarized signals. So right here, your signal is going to radiate off of this element, and it's going to radiate with an electromagnetic field that comes off of there, and these little electrons or little magnetic particles are lined up in a vertical fashion as they leave this antenna because it is vertically configured or vertically oriented. So this is a vertical polarization. Now if I flip this over on the other side where the elements are going this way, it's going to be a horizontally the antenna is going to, the signal is going to be horizontally oriented, okay? So, and that's important because if you're talking locally to somebody and you're on a vertical polarization and they're on a horizontal polarization, you're going to not be able to talk to them very well because you have a humongous amount of dB loss or dB attenuation between your signal and theirs. Now, when you talk skip, here's the thing. When you're talking long distance, your signal's going up and bouncing off the ionosphere. Funny things happen to polarized signals at that point. They can leave the transmitting station vertical, and they might land at the receiving station several hundred miles away, horizontally polarized. So sometimes they switch and they tumble and turn, and sometimes they can come down being polarized in a different fashion than where they left. But basically speaking, for 2 meter single sideband, which is what this beam is going to be used for, we talk with horizontally polarized signals. The other night, some of my friends and I were talking across town really well on 2 meter sideband, but it was because we were both running vertical. We just happened to be. That's the way we were set up. But again, I'm fixing this up for field day, and I'm going to have it to where it is polarized. When I put it back on the mast, it'll be polarized or oriented horizontally. So I hope that helped you. Again, just kind of a little recap here. Our signal's coming in here. It's going out the radiating element, or the guess I can't even remember anymore, Julian, forgive me. But you got your director elements here, and this is your radiating or driven element is what that's called. And then of course this being your reflective elements here. Pushing that signal or reflecting that signal to where it'll go out this way, and following the direction of that. So anyway, I'm going to go ahead and join the net. They're coming on right now, but I hope you got something out of this. And if you have any questions, be sure to text them or email them to me, and I'll try to help you out. I love you. I hope this was helpful to you, and we will talk to you later. Love you. Bye-bye.